Hey guys, so welcome back. Let's try the section B of the Physics 2024 exam. Let's see how we go. Okay, question number 1. So, tugboats often have to tow around boats around the port of Melbourne. Okay, boat 1, a tugboat with mass of this, is towing two larger boats as shown in figure 1. All three boats are moving in a straight line. Boats 2 and 3 do not have their engines on. Okay. Boat 2 has a mass of 5 times 10 to the power of 5 kilograms, and boat 3 has a mass of this. The resistance force of this acts on the boat 2, and resistance force of this acts on boat 3. The tension in rope 1 is this. Okay, show that the acceleration of the two boats being towed, boat 2 and boat 3, is 6 times 10 to the power of minus 2. Okay, we'll just use our F equals to ma, so F is equals to ma. Okay, now that means ma has to be equal to all of the other forces. So just imagine that we are only looking at this part over here to find the acceleration from, and of course also the rope, like all of this over here. Okay, so our mass for this, which is the m over here, is just going to be the mass of the two ships added together. So 5 plus 6 times 10 to the power of 5 times a has to equal to all of the other horizontal forces. So I'm going to say that my right is positive, so that means 9.2 times 10 to the power of 4. Maybe I'll write it this way. So 9.2, which is positive as it's acting to the left, then friction, which is this over here and this over here, to the right, so that means they are negative. So minus 1.2 minus 1.4 times 10 to the power of 4. So that means our acceleration is basically going to be let's put this in my calculator, I'll just get it. Okay, so it's 9.2 minus 1.2 minus 1.4. So I'm getting 6.6 times 10 to the power of 4 divided by 11 times 10 to the power of 5, and this should hopefully give me the acceleration that we need to find. So 6.6 times 10 to the power of 4 divided by 11 times 10 to the power of 5. Yes, I indeed get 6 times 10 to the power of minus 2 meters per second squared. Okay, hopefully that made sense. So moving on to the next question. Calculate the tension T in rope 2, show your working. Okay, so for that we need to find the tension of this rope, right? So what is this rope basically carrying? This rope is responsible for this part, correct? So the tension is basically the mass times acceleration of this boat over here, and then also the friction, because it has to pull boat 3 as well, right? So friction and the mass times acceleration of boat 3 itself is going to be the tension. So our tension is equals to mass of boat 3, so which is 6 times 10 to the power of 5 times the acceleration that we found to be 6 times 10 to the power of minus 2 plus the friction, which is 1.4 times 10 to the power of 4 newtons. And if I were to put this in my calculator, let me just do that real quick. So 6 times 10 to the 5 times 6 times 10 to the minus 2 plus 1.4 times 10 to the 4. So I get 5 times 10 to the power of 4 newtons. So 5 times 10 to the power of 4. Okay. Engineers are testing a new high-speed vehicle, EV, on a high-speed test track. In one test, the EV travels around a circular banked arc with a radius of 1.2 kilometers. The angle of the bank is 33. This is shown in figure 2. Okay. Calculate the maximum speed the car can travel around this bank track if no sideways friction between the wheels and the track. Okay, so in that case, let's just quickly label the forces real quick. So we'll have our mg like this, and then we have our normal force going like this. So that means that this component of the normal force, so n cosine theta, basically, n cosine theta is responsible for cancelling out the gravity, and the other one, which is the centripetal force, like this, so which is the n sine theta. So here basically n cosine theta will cancel out with mg, and our n sine theta will become our centripetal force. So based on that, we can write these expressions down. So n cosine of theta is equals to mg, n sine of theta is equals to mv squared on r, because this is the centripetal force, right? So that means n is equals to mg cosine theta. And now if I were to place this back in here, I'll get mg sine theta divided by cosine theta is equals to mv squared on r. So we'll get mg tangent theta is equals to mv squared on r. So our m and m will cancel out. So we'll have v squared is equals to rg tangent theta, and v is square root of rg tan theta. So now we can just plug in the values. So v equals to square root of, what's the radius? 1.2 kilometer, 1.2 times 10 to the 3 times the gravity, 9.81, times tangent of 33. So let me put this in my calculator. So I'll get 1.2 times 10 to the 3 times 9.81 times tangent 33. So I get 87.43 meters per second. 0.43. So the reason why I've actually done all of this deriving, because you already know about this formula, but the reason why I've done all the derivation is because it's 3 marks over here. So I thought maybe it's better to do it than, lose our marks for not showing enough working out. Alright, explain how the normal force from the banked track provides the centripetal force on the car. Okay, so the normal force, I already mentioned about this briefly just before. The normal force on the banked track has a horizontal component and sine theta, which provides the centripetal force. Okay, so next question. Okay, this page is blank. Okay, cool. Okay, we have a quadratic. So a golf ball near the edge of a cliff is hit at a speed of 48 meters per second at an angle of 35 to the horizontal as shown in figure 3. Yep. The golf ball lands on the ground 6.2 seconds after it is hit. Ignore the air resistance. Determine the height h of the cliff. Okay, so we are given, what are we given? We are given the initial velocity. We are also given the angle, and then we are given the time taken for it to reach here. So time taken for the journey basically. And we are asked to find the height. So that means we can just say that h is equals to ut plus half at squared. Right? So our u is going to be the vertical component of this velocity. So that would basically be 48 sine of 35. our time is already given, so times it by 6.2, and then substitute the gravity in, so minus half times 9.81 times the t squared, so 6.2 squared. Now the reason why this becomes minus all of a sudden is because I have defined up and right as positive, so I'm going to say this is positive and this is positive, and since gravity is acting downwards, we have to say that g is going to be negative, making this a negative. Okay, so let me put this in my calculator and see what I get. So h has to be 48 times sine 35 times 6.2. Okay, and then take away 0.5 times 9.81 times 6.2 squared. Okay, so I get height as negative 17.85 meters. Now, again, the height is negative because we traveled downwards. So our initial starting point was here, and then our final point was here. So we did travel h distance down, so that's why our height is negative. So we only need to get the magnitude of the height, so 17.85 meter will do here. So 17.85 meters. Okay, calculate the horizontal distance that the golf ball travels before it reaches the ground below. Okay, so we know that delta x is equals to ut again. So this time our u will be the horizontal component of the velocity. So it's gonna be like this and like that. So this is our vertical v of y, and this is our horizontal v of x. So we need our horizontal component. So we'll have 48 cosine of 35 times 6.2, and that should give us the horizontal distance. So let me just put it in my calculator. So 48 cosine of 35 times 6.2. So I get 243.78 meters. 243.78 meters. Okay, describe how in real life air resistance would affect the golf ball's flight path. Okay, so in real life, the air resistance opposes the motion of the ball hence the maximum horizontal and vertical distance ball travels will be less than that without air resistance. Without air resistance, I'll also draw a picture just to show my understanding in case if my wording sounds confusing. So I'm just going to say that path with and without air resistance is shown below. So let's quickly draw our diagram. Alright. Okay, that will do. And this is the without resistance one, so something like this. So this is without resistance, and this is with resistance. Okay, moving on to the next question. So question 4, the safety of the passenger car can be assessed during using simulated collisions with a crash test dummy in the passenger's seat. Figure 4 shows a dummy without a seatbelt in a car traveling towards a fixed solid wall. Okay, during an initial test, the dummy is seated in a car with no front airbags fitted. When the car hits the wall, the dummy experiences a force as it collides with the interior dashboard of the car. This force varies with the time as shown in the graph in figure 5. Okay, so what I meant to do, so determine the impulse on the dummy during the initial test. Okay, so we know that the area under the force and time graph is going to give us the impulse. So we just have to simply find the area here, and that will be good. So J is equals to 2 times half. Oh, well, this is 2 times because I've divided the like triangles into 2 parts. So I can have like the right angle triangle times the maximum height, which is, what's the scale? So 1, 2, 3, 4, 5. So 200, 2000 space for each bar. Okay, so this will be 24k. And what about this one? 1, 2, 3, 4, and 5. Okay, so this will be 120. Alright, so 2 times half times the base, which is 120. Wait, hold on, what's the units? Yeah, okay, there we go. So that's the trick. So this is the milliseconds, sorry. And we need to convert that into seconds first. So we have to times it by 0.12 times 24,000 Newton, right? Yeah, okay. So now, if I were to put that in my calculator, so 24,000 times 0.12, I get 2880 Newton seconds. So 2880. Okay. In a second test, the dummy is seated in an identical car, traveling at the same speed, okay, as the initial test. Again, not a seat belt, but with front airbags fitted. The collision duration for the dummy in this second test, as it collides with the airbag, is double the time of the initial test without the airbags. The results of the initial test are shown as the dashed lines. Okay, sketch on the figure 6 how force on dummy could vary with time during this second test. So we are given that the time doubles, right? So that means if the time is doubled, we have to halve our force to maintain the same impulse created, basically, because it's traveling at the same speed as the initial test. Yeah, so our time is doubled. So what's our current time? So it's 240. So our new time will be somewhere here, and the midpoint would be here. And what is our maximum? So this was 24,000. We divided by 2, we have 12,000. So it will be like this, basically. So let's just draw the line. Maybe I'll use a different color. So from here and then here. So something like this would, I think, be acceptable. Okay. And yeah. All right. So next question. Question number 5. A basketball of mass 0.63 kilograms traveling vertically down hits the floor at a speed of 12 meters per second and rebounds at a speed of 10 meters per second as shown in figure 7. Calculate the magnitude and direction of the change in momentum of the basketball. Okay, so change in momentum is just mass times final velocity minus the initial velocity, right? Okay, so mass of the ball is 0.63. Our final velocity is 10 meters upwards, and initial velocity is 10 meters downwards, so negative 12 here. And this would be 0.63 times by 22. So if I were to put that in my calculator, so 0.6, sorry, not 3663 times 22, I get 13.86 kilogram meters per second. Just making sure unit is all good. Yep. Okay, so our answer would be 13.86 kilograms meters per second, and direction is going to be up because after rebounding it's going to go up. So yeah. Okay. And moreover, just further explaining, because the answer is positive, we know it's definitely going to go up because we have defined up as positive. Okay. In the collision, is the collision elastic or inelastic? Justify your answer. No calculations are required. So we know that since V final is not equals to V initial, it implies that the final and initial kinetic energies are not the same, and hence collision was inelastic. Okay. Yeah. So question number 6. So Jenny and Kawan are discussing how International Space Station supply craft missions operate. The station is resupplied with food, water, air, fuel, scientific equipment, blah 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 blah, and other necessities for 3. Okay. Kawan suggests that the supply craft could initially be put into circular orbit relative to ISS as shown in figure 8 before it eventually docks. Okay. The centripetal force needed to keep the supply craft in orbit, Kawan argues, is provided by the gravitational attraction between the supply craft and the ISS. Sorry. Kawan calculates that an orbital radius of 500 meters could be achieved with the supply craft traveling at a speed of 0.436 meters per second. The mass of the ISS is this, and the mass of the supply craft is this. Okay, will Kawan's suggestion work? Justify your answer with appropriate calculations. So we basically have to actually calculate the centripetal force that is required, and then we have to see if the gravitational force actually exceeds that. So let's start by calculating the centripetal force. So Fc is equals to, what is it? mv squared on r. Okay, so we have our small m, which is the mass of the supply craft, so 1.5 times 10 to the power of 4, and we are given the velocity of 0.436 and square. And what's our radius? Well, okay, what's our radius? Radius is 500 meters. Okay, so let's calculate that. Let me put that in my calculator. So 1.5 times 10 to the power of 4 times by 0.436 whole squared divided by 500. So we get 5.703 newtons. And now we have to find out the the gravitational attraction. So basically Fg, which is equals to gmm on r squared. So our g is just a constant, which is going to be 6.67 times 10 to the negative 11 times by what is the mass? Yeah, so the big M is the mass of ISS, so 4.5 times 10 to the power of 5, and the small m is the mass of supply craft, so 1.5 times 10 to the power of 4 divided by 500 squared. 500 squared, and let me put that in the calculator again. So 6.67 times 10 to the negative 11 times by 4.5 times 10 to the 5 times by 1.5 times 10 to the 4 divided by 500 squared. 100 squared. Okay, so I get 1.8 times 10 to the negative 6 newtons. Okay, sorry. Now, well, obviously this force, the required centripetal force, is much higher than what the gravitational attraction is. So that's why so since Fc is greater than Fg, Kawan's suggestion will not work. Not work. Okay? Yeah, so because centripetal force, so this is the required centripetal force for it to actually work it out. But since the gravitational attraction, like Kavan suggested, is enough for the centripetal force, no, it's not. It's actually way less, so that wouldn't work out. Okay? So next question. So question 7. An electron is accelerated from rest through an electric field. It enters an area of constant magnetic field B of magnitude this, which is perpendicular to the electron's path. Once within the magnetic field, the electron flows a circular path of radius this, as shown in figure 9. You may ignore the relativistic effects. Okay. Show that the electron speed v as it enters the magnetic field is 1.32 times 10 to the 7. Okay, so we know that the radius is going to be mv on qb, and we are finding the velocity, so v is equals to r qb on m. So that's why our v is equals to, what's our radius? So 1.5 times 10 to the negative 2, I'm converting it into the meters, times q, which is the charge, so 1.6 times 10 to the negative 19, times the magnetic field, which is 5 times 10 to the minus 3, all over the mass of an electron, which is 9.11 times 10 to the negative 31. So let me put that in my calculator, and hopefully it gives me this. Okay, so 1.5 times 10 to the minus 2 times 1.6 times 10 to the minus 19 times 5 times 10 to the minus 3 divided by 9.11 times 10 to the minus 31. Yep, so it gives me 1.3172 blah blah blah, which is same as 1.32 times 10 to the 7 meters per second. Okay. Calculate the accelerating voltage needed for the electron to reach the speed of 1.32 times 10 to the 7. Okay, I guess we can use the work done essentially. So work done is equals to half mv squared, which is also equals to q times the voltage. So half mv squared is equals to q times the voltage. So voltage is equals to mv squared divided by 2q, which is equals to 9.11 times 10 to the minus 31 times by 1.32 times 10 to the 7 squared times 2 divided by 2 times 1.6 times 10 to the minus 19. So let me put that in my calculator. So I get 9.11 times 10 to the minus 31 times that whole square 2 times 1.6 times 10 to the negative 19. That gives me, so voltage is 493.96 is my answer. Okay, 493.96 should be good. Okay, the electron is replaced by a proton traveling at the same speed. A proton has a mass of 1.67 times 10 to the negative 27 kilogram, okay, and a charge of this, positive. So describe the path that the proton takes after entering the constant magnetic field compared to the path taken by electron. Justify your answers, no calculations are required. Okay, so we know that R is equals to, what was it, mv on, what was it, qb, there we go, mv on qb. Okay, so all of this is basically constant, so vq and vqb are all constant. So that means R is proportional to the M. Okay, so since the mass of a proton is greater than mass of electron, therefore the radius will increase. Radius will increase, right? That's one thing that will change. So that's one of the change. The other change is that because the charge changed, so now the proton will rotate in the other direction. So since the charge is positive, now positive, the proton will how do I say it? So rather than it, rotating this way like an electron, it will now rotate this way. So I guess maybe I can say it, the proton will rotate in the opposite direction. I guess that will do, but hopefully that makes sense. So basically my idea is saying that because the charge changed, because electron is negative and proton is positive, if electron is rotating this way, then proton will rotate this way. Okay, that's what I'm trying to say by the second point. The first point, so this one is just showing the radius will increase basically. That took me a long time, but anyway, so hopefully that makes sense. So electrical activity in thunderstorms can be modeled as charge separation causing an electric field to form between the base of the thundercloud and the ground, similar to two charged parallel plates. Figure 10 shows the base of a thundercloud that is 850 meters above the ground. Okay, using arrows, sketch on figure 10 at least 5 electric field lines between the ground and the base of the thundercloud. Okay, so we have to sketch 5 field lines. So make sure that it's going from positive to negative, of course, like that. 1, that's 2. I'll just copy and paste, easier that way. 3, 4, and I'll draw one last one, and 5. So make sure that they are parallel as well. Okay, alright. The potential difference between the ground and the base of the thundercloud is 1.2 GeV. Okay, calculate the magnitude of the electric field between the ground and the base of the thundercloud. Okay, well, we can just use that E equals to V on D. So we have 1.2 times, I believe that's 10 to the 9, divided by the distance, which is 850. Okay, so let's see what the answer is. 1.2 times 10 to the 9 divided by 850. Okay, so I get 1.41 times 10 to the 6 V on M. So 1.41 times 10 to the 6 should be the answer. Okay, so next question. A 1.2 GeV bolt discharges to Earth from the thundercloud with a current of 30 kiloamps for a duration of 60 microseconds. Calculate the total energy transferred by this lightning bolt. Give your answer to 3 sig figs. Okay. So we know that Q is equals to IT, right? And W is equals to QV. So we can say that W is equals to IVT. So that means our current is 30 times 10 to the power of 3. We times that by voltage, so 1.2 times 10 to the 9, and by time, which is 60 times 10 to the power of minus 6. Okay, let me put that in the calculator. Okay, so 30 times 10 to the 3 times 1.2 times 10 to the 9 times 60 times 10 to the minus 6. So I get 2.16 times 10 to the 9. So 2.16 times 10 to the 9. Oh yeah, 3 sig figs. Yeah, that's good. 3 sig figs. Okay. Next question. Students build a simple DC electric motor consisting of a coil of wire and a uniform magnetic field. The coil is initially at rest, and orientated in a horizontal position as shown in figure 11. The coil can be rotated about the axis of rotation. Describe one orientation of the coil, if any, where magnetic force on the side FG is 0. Okay. I guess that happens when the magnetic field is parallel to FG, basically. Yeah, so I'm just gonna say that when FG is parallel to the magnetic field, or actually when magnetic field, it's good, is parallel to magnetic field, it will not have any force acting on FG. Okay. Describe one starting orientation of the coil, if any, where the coil will not start to rotate from rest. Okay, so I guess if the coil is vertical, I don't think it will rotate then, because there will be no torque generated, essentially. So what I mean is that currently, if I were to do this, because the magnetic field is going like that, yeah, so when FG is basically perpendicular to the magnetic field, no torque will be generated, essentially. Yeah, I'm just gonna write that. I'm actually a bit confused, but okay. When FG is perpendicular to the magnetic field, no torque will be generated, and hence coil will not rotate, and hence coil will not rotate. Suggest one way that the torque of the DC electric motor could be increased using exactly the same single coil and the same 6-volt battery as shown in figure 11. Well, I mean, torque is basically force times the perpendicular distance, basically. So we can't increase the perpendicular distance, but we can increase the force, right? So force is equals to NBIL. So I'm just gonna ignore N because that's gonna be constant. because, you know, same single coil, so N is going to be constant. Yeah, so F is proportional to B, F is proportional to I, and F is proportional to L. So basically, if you're using the same coil, L kind of is irrelevant. Yeah, we'll just go with B. So if we hence by increasing the magnetic field strength, we can obtain more torque. We can increase the torque. Okay. Describe one orientation of the coil, if any, where the magnetic force on the side FG is 0. Actually no, that actually makes sense. So like, yeah, when FG is parallel to the magnetic field, it will have 0 force, because I think force is basically like BIL, and there's also like an angle component here. So basically, if the angle is 0, the whole thing just becomes 0, right? So that's why I think, yeah, FG parallel to the magnetic field makes total sense. Yep. So that's the intuitive understanding, or maybe logical understanding. Describe one. Yeah. So if like if there was any, if we want to prevent any rotation, we know that torque is equals to force times the perpendicular distance, as I just mentioned before. So currently it will rotate. So let's say at this point, right? So if I were to, this is our perpendicular distance, and the force is currently pointing down, right? Or pointing up, let's say. It doesn't really matter. Our perpendicular distance D is like this, basically. Now, what happens if the coil is at a vertical position? So it's like here, and then here. Okay, well, my drawing is so good, I know. Okay, anyway, so never mind, I can explain without the drawing. So if the coil is vertical, I can't even draw a vertical coil. So essentially what will happen is the force will still point downwards, like if the coil was vertical. Okay, like, okay, I literally cannot draw a vertical coil. So if I go like this, maybe like that, and like this, I guess that kind of looks like a vertical coil. Anyway, so here, as you can see, that this distance, like, it's not perfectly vertical, but if it was perfectly vertical, the force will still go this way. Right? However, this distance is no more perpendicular, it's rather parallel, so like it kind of will not rotate because there's no torque generated, if that makes sense. Yeah, sorry guys, my drawing is not the best. Yeah, okay. Alright, yeah, part C makes sense. So let's move on to the next question. Page is blank. Okay, so two physics students, Aroha and Tyler, are investigating the electromagnetic induction. They use apparatus shown in figure 12, which consists of a single coil of wire in uniform magnetic field connected to the slip rings X and Y. Explain the purpose of this slip ring shown in figure 12. Okay, so slip rings allow coils to continuously spin without tangling the wires, right? Then it also maintains a constant connection between the circuit and the coil, and furthermore it also reverses the current and force every half period, basically, keeping the torque in same direction. Okay. Tally rotates the single coil of wire within uniform magnetic field at a constant rate, while Aroha measures the output voltage versus time on an oscilloscope. The oscilloscope display is shown in figure 13. Okay, from the oscilloscope trace shown in figure 13, determine the peak-to-peak voltage produced by the apparatus and the frequency of the rotation of the single coil. So peak-to-peak voltage is basically this distance over here. So 4 plus 4, which is 8. So peak-to-peak voltage is going to be 8 volts. And we have to find the frequency. So we know that the period, so this is one period of the graph, right? Because it's a sinusoidal or trigonometric graph, so it has a period of 0.2. And we know that frequency is 1 on period, which is 1 on 0.2. So if I were to put that in my calculator real quick, I don't want to make any silly mistakes. So I get 5. Okay, so frequency is 5 Hertz. Alright. Tyler makes a modification to the apparatus in figure 12. Aroha sees the new oscilloscope trace as shown in figure 14. The dotted line shows the original voltage before any changes made by Tyler. Okay. Explain 2 possible ways Tyler could have modified the apparatus to create the oscilloscope trace shown in figure 14. Justify your answer. Right. Okay, so here we can see that period is the same. The area also doesn't change. The area of the coil, right? Yeah, the area, yep, it doesn't change. Okay, so we can use this formula that is equals to n times change in flux over change in time. I mean, normally there is a negative in front of it, but we are just only looking for the possible changes, not the value, so that should be fine, right? So our change in flux is basically B times A, so n equals to B times A over change in time. Now, as I mentioned already, that area and time are just constant, so we don't have to mess with them. So here we can see that our amplitude has doubled, essentially, is the change. So I guess we can say that our is proportional to n, and this is also proportional to b. So that means 2 possible ways are double the coil, double the turns in the coil, maybe, and double the strength of magnetic field Okay, now the reason again why time is constant is because, well, the period doesn't change. The period is still constant, it's still 0.2. Okay, so that's why time is constant, right? And the area of the coil doesn't change because, well, they didn't mention anything about that. So that means area and change in time is constant, and that's why we can get the proportionality. And yeah, that's how I got the answer. Okay, so next question. sorry. Jia charges a 36 volts battery used for her electric bike from a mains 230 VRMS power point. The transformer part of the battery charger circuit is shown schematically in figure 15. Assume that the transformer is ideal. Calculate the number of turns required on the secondary coil if there are 460 in primary coil. Okay, so I guess we can just use the N1 divided by N2 is equals to V1 divided by V2. So our N2 is what we are finding, so that is N1 times V2 divided by V1. Okay, so N2 is equals to 460, which is already given. N1 is 460, which is already given, times V2, which is 36 over 230. So that can get cancelled out. So N2 is equals to 72. So 72 turns, basically. 2 turns. Okay, the RMS output current from the transformer to change the battery is this. Okay, calculate the RMS input current to the transformer. Right. So if everything is just in RMS, we can just use V1 I1 equals to V2 I2. And what we are finding? We are finding the input current. So I1 is equals to V2 I2 divided by V1. So we'll have V2, which is 36 times 0.80 divided by V1, which is, what was it again? 230, yep. Which is equals to, let me put down in my CAS, not CAS, I mean the calculator. Okay, I've been doing way too much maths these days, so 0.80 divided by 230. So I get 0.125 amps roughly. So yeah, 0.125 amps. Okay, next question. So explain why the transformer requires AC input and would not work if the input was a constant DC. Okay, so constant current in the primary coil produces a constant magnetic field since magnetic flux is constant, no EMF is induced, basically. And you can also write this n d phi dt, and since the change in flux is 0, induced EMF is also 0. So yeah, since change in flux is needed, having a constant DC input would not work. Hence, the transformer requires an AC input. Okay? Constant current in the primary coil produces constant magnetic field. Since magnetic flux is constant, no EMF is generated or induced. Yep. Since change in flux is needed, having a constant DC input would not work. Hence, the transformer requires an AC input. Okay, guess that makes sense. Yep. Alright, so question number 12. A general store in country Victoria is connected to the mains 230 volts electricity supply. The owners decided to install an array of solar photovoltaic PV panels to decrease their electricity bills. Fair enough. The maximum output of PV panel, each PV panel is 600 watts in full sunlight with a maximum voltage of 20 volts. With a maximum voltage output of 20 volts, okay? The owners install 50 panels connected in 10 by 5 array as shown in figure 16. The array consists of a bank of 5 strings connected in parallel with each single string consisting of 10 PV panels connected in series. The total output of array is connected to an inverter. Okay. Let's calculate the maximum possible total output power from this array. Okay, so each of them, each panel has 600 watt in full sunlight. Okay. So then each string here would basically have 600 each, right? So that means per string we got 6 kilowatts. So we got 600 for each panel, and then we have each string, so times by 10. So because each string has 10, I believe. Yeah, 10. And then we got 5 strings like that. So I'm gonna say it's 30,000 watts or 30 kilowatts maybe, as they want it in kilowatts. Yep, 30 kilowatt. Well, that was not needed. Okay. The maximum output of each PV panel is rated 600 watts in full sunlight with a maximum voltage output of 20. The owners installed 50 panels connected in 10 by 5 array as shown in figure 16. The array consists of a bank of 5 strings. Okay. Yeah, I'm gonna go with 30 kilowatts as the maximum output power, because each of them has 600 watt in maximum sunlight, full sunlight basically, and we got 10 in each string. We got 5 of them, so I'm gonna say, yeah, 30 kilowatts is good. Okay, calculate the maximum output voltage and maximum output current from one string of 10 PV panels connected in series in full sunlight. Show your working. So now we are working with individual string basically. So how much okay, so each of them has a voltage output of 20. Now in series, current stays constant but the voltage changes. So 20, 20, 20, and then we have 10 of these. So in total there'll be 200 here as our maximum output voltage from one string, because we have 10 of them and each of them can have 20 volts as the maximum voltage output, right? And because in series they'll add up, right? So it will be voltage maximum is equals to 20 times 10, which is 200 volts, and we also have to calculate the maximum output current. So our current in series, so our current will stay constant throughout here. Okay, so what I'm gonna do is, we know that our power is equals to VI, right? So I is equals to P on V. So each of them has 600 watts and 20, right? So let's put that in. So 600 watts over 20, so we'll get 30 amps as our maximum output current basically. Okay, so we'll have 200 volts and 30 amps. determine the maximum output voltage and maximum output current from the whole array in full sunlight. Okay, well, so maximum output voltage doesn't change because each of them will have 200, 200, 200, and 200, right? So they're in parallel, doesn't change. Maximum is going to be 200 volts. And for current, so we got 30 amps as our current. So in series, current will be constant and the same. So each string will basically have 30 amps throughout. And we have 5 of them. So again, we'll have total of 150, essentially. 150 amps. So 30 times 5 is 150. Okay? So our total current is 150 amps. Hopefully that makes sense. What is the function of the inverter? So, well, basically, it basically just converts DC power to AC, essentially. So converts the DC power generated by panels to AC, so that they can basically use the power, basically. Okay, this is an interesting question, actually. Yeah. Okay. So when energetic cosmic rays from the space interact with Earth's upper atmosphere, subatomic particles known as muons are produced. These muons are unstable, have been observed to rapidly decay. They decay with mean life of this, okay? As a result of their short half-life, As a result of their short life, physicists have used muons produced in Earth's upper atmosphere to test Einstein's special theory of relativity. In one experiment, physicists placed a muon detector at the top of a mountain at a height of 6,500 meters. Okay, the muons produced in the upper atmosphere at a height of 9,700 meters above the Earth's surface travel downwards at a speed of this. Okay, so using classical mechanics, show that a muon would reach the muon detector at the top of the mountain in 10.8 microseconds. Okay, well, so V is equals to S on T, and that means time is equals to S on V. So our distance is going to be this distance, basically, just from here all the way to here. So this is our distance, so this is our S. So that means our S is basically just 9,700 minus 6,500 divided by our velocity, which is 0.985 times 3 times 10 to the power of 8, basically, because it's speed of light, right? So if I put this in our calculator, we should hopefully get what is required. So 9700 minus 6500 divided by 0.985 times 3 times 10 to the power of 8. So I get 1.08 times 10 to the power of -5 seconds, which is indeed 10.8 microseconds. Okay? According to classical mechanics, is a muon likely to reach the muon detector on top of the mountain? Justify your answer. Sorry, guys. Okay. So since the mean life of muons is 2.2 microseconds, and the time taken to reach sensor is 10.8 microseconds, which is like roughly 5 times. 5 times. 5 times maybe mean life of muons. it is very unlikely, basically, as muons will decay. Okay, so experiments conducted by physicists show that a significant number of muons created at a height of 9,700 meters above Earth's surface and traveling at the speed of light consistently arrive at muon detector at top of the mountain. Okay, calculate the Lorentz factor for a muon traveling at this. Okay, so Lorentz factor is equals to 1 divided by 1 minus v squared on c squared, which is equals to 1 on 1 minus 0.85 squared c squared divided by c squared. So this and this will cancel out, leaving us with 1 divided by square root of 1 minus 985. Okay, so squared, of course. Plugging that in our calculator, let's see what we get. So 1 square root of 1 minus 0.895 squared, we get 5.795. So I'm just gonna say 5.8 as our Lorentz factor, or maybe I'll use 5.795. Okay, what is the mean half-life of muon in physicists' frame of reference? So well, for physicists' frame, they will experience proper length but dilated time. So t is equals to gamma times t0. So 5.795 times 2.20, which is equals to 12.7 microseconds, basically. So that is the okay. Explain how the Einstein special theory of relativity accounts for the experimental evidence that a significant number of muons created at a height of this, traveling at the speed of this, consistently arrive at the muon detector at the top of the mountain. Okay. Einstein special theory of relativity accounts for this experiment, in a way that because in the physicist what's the spelling? physicist frame of reference, proper length, or maybe I should say proper distance is measured. However, the time measured is dilated. Therefore, muons will have a longer half-life and are able to reach the muon detector maybe to make it a bit more related to the context, what I'm gonna do, muons created at a height of 9700 meters will have a longer half-life and are able to reach the muon detector traveling at a speed of 0.985 c. Okay, Einstein's special theory of relativity accounts for the experiment because in the physicist's frame of reference, proper length distance is measured. However, the time measured is dilated. Therefore, the muons created at a height of 9700 meters will have a longer half-life and are able to reach the muon detector traveling at a speed of 0.95 c. Okay. To reach the muon detector, maybe I'll remove that and put it here at height of this, and traveling with speed of 0.985 c. Sorry, it looks so messy, but basically, yeah, so right after this section you have to put this, you have to read this over here basically. Okay, and then I'll put an arrow saying that you can go back here. Okay. Alright. PET scanners are used in medical imaging. They rely on an electron and a positron colliding and completely annihilating each other to produce two gamma rays. The electron and positron have the same mass. Assuming that the electron and the positron are traveling at a negligible speed when they collide, calculate the total energy released in the annihilation. Okay, well, so that is just E equals to mc squared, and completely annihilating meaning that all the energy is basically released. So mass, we have 2 times 9.11 times 10 to the negative 31 times, put the bracket, 3 times 10 to the power of 8 squared, because, well, they have the same mass, so that's why I times it by 2. So putting that in my calculator, so 2 times 9.11 times 10 to the minus 31 times 3 times 10 to the 8 squared. So I get 1.64 times 10 to the minus 13 joules. 1.64 times 10 to the minus 13 joules. Okay. 2 gamma rays produced travel in opposite direction with exactly the same wavelength and energy as shown in figure 18. Explain why gamma rays travel in opposite direction. Okay, well, to give you a real life example, let's say you and your friends, throw a basketball at each other and somehow they collide in mid-air. What happens to both of the basketball? They'll collide and go back in different directions, right? That's the same thing that happened here, and that happened because of conservation of momentum. Okay, so due to conservation of momentum. Okay, hopefully that made sense. Right. Oh, okay, question 15. An electron gun forms a part of transmission electron microscope, which uses the wave properties of electron to study specimens that are too small to be observed using an optical microscope. Figure 19 shows a beam of electrons passing from an electron gun through 2 plates, plate A and plate B. The electron reach plate A with a negligible speed and are accelerated by potential difference between the plates V0, emerging from plate B with a speed V. Okay. Sorry. The de Broglie wavelength of the electrons in particular beam is this. Calculate the momentum of an electron in the beam. Okay, so that would just be P equals to H on lambda. So we'll have H is 6.63 times 10 to the minus 34 divided by the wavelength that we have, which is 2 times 10 to the power of minus 10. And that, let me put on my calculator, 6.63 times 10 to the minus 34, 2 times 10 to the minus 10. So that is equals to 3.315 times 10 to the minus 24 kilogram meters per second. 3.315 times 10 to the minus 24. The electron beam is passed through a crystal with an interaction with an interatomic spacing of 3 times 10 to the negative 10. Okay, two physics students Sally and Max are discussing their predictions for different patterns produced by the electron beam. Sally claims that since the wavelength is less than the interatomic spaces, there will not be a detectable diffraction pattern. Max disagrees and claims that they will obtain a useful diffraction pattern. Okay, so we are basically checking out the diffraction, what the extent will be. So if you remember, diffraction is what? Is proportional to lambda over w, right? Where lambda is just the wavelength that we have, which is just that, the Broglie wavelength, and w is the interatomic spacing. So it will be 2 times 10 to the negative 10 divided by 3 times 10 to the negative 10. Oh, that would cancel out. So 0.667 basically. So in this case, some spread will be observed. Some spread will be observed basically, because the closer it is to 1, the better it is, right? So basically what I've learned is that if lambda on w is less than 0.1, then little or no spread. If lambda over w is between 0.1 and 1, oh sorry, not including 1, then there will be some spread. Although if lambda over w is greater than or equal to 1, then very good spread. So basically, since the spread is still relatively close to 1, I'm going to say some spread is still observed. So I'm going to say Max is correct. And maybe I'll add my reasoning that as 0.1 less than lambda on w less than 1. Okay. Sally and Max now change the potential difference in the electron gun to generate electrons with an energy of this and corresponding de Broglie wavelength of this. Okay, so this adjusted electron beam is then directed through a tin foil, resulting diffraction in this. Okay, the students decide to contrast this pattern with the pattern produced by passing X-rays through an identical foil. Okay, they know that electrons and X-ray produce patterns with same dimensions. Okay, fair enough. Explain how the electrons and X-rays can produce almost identical patterns. Well, moving electrons exhibits wave properties and have a de Broglie wavelength. Therefore, electrons can have diffraction which depends on lambda on w, as we discussed. So if wavelengths of X-ray and electron are same, it creates, or maybe I should say it produces, to make it relate back to the question, it produces almost identical patterns. Okay. Calculate the energy in EV of the X-ray photons used to produce the image shown in figure 20b. Okay, so that's easy. So E is equals to H lambda on C. Wait, no, HC on lambda. HC on lambda. Okay. Now because we are finding in EV, we have to use the other one. So 4.14 times 10 to the minus 15, I believe. Times by C, which is 3 times 10 to the 8 over the wavelength that we have, which was 5.01 times 10 to the negative 11. So let's put that in our calculator. So 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by 5.01 times 10 to the minus 11. So I get 2.48 times 10 to the 4 eV basically. Okay, so 2.48 times 10 to the 4. Okay, so Nicola is conducting an experiment to investigate the photoelectric effect using the apparatus shown in figure 21. She uses various filters to shine electromagnetic radiation of particular frequencies on the photocell. Okay, Nicola increases the voltage until the current reaches 0, okay, and records this voltage. She repeats this process for different frequencies. The variables in this experiment can be classified as controlled, dependent, or independent. Complete the table below by providing one variable from the experiment for each classification. Okay, so controlled. She uses various filters to shine this. Okay, increases the voltage. Until the current reaches 0. Okay. So I guess dependent is voltage. Oh wait, no, dependent is, wait, so she uses various filters to shine electromagnetic radiation of particular frequencies on photocell. Nicola increases the voltage until the current reaches 0. I guess current is dependent on voltage, so I'm gonna say that independent is the voltage and dependent is the current. Controlled, so filters are also changing. I guess we can say metal plates because that stays the same, right? Okay, so metal plate. Guess that stays the same. Yeah, so control variable is basically something that stays the same throughout the experiment, which is control. Yeah, I think metal plate is good for this. Okay. Nicola's results for the experiment are shown in the table below. Okay, so the uncertainty in the measurement of the voltage is this. Okay, on the axis below, plot Nicola's data, including uncertainty bars, and draw a line of best fit. Okay, so at 6 is 0.1. So what's the scale 1? Okay, so just here, and this is the uncertainty bar. At 7 is 0.5, so here, that and that. 8 is 0.9, so here, that and that. 9 is 1.2, so that's here. Wait, hold on, am I getting the scale right? 1, 2, 3, 4. Yeah, it's good. Okay. Is 1.2, which is here. And of course the uncertainty bars. Okay, and then 10 is 1.4. Okay. So just here. Okay. Okay, so now we draw the line of best fit. Like that. Guess that would do, kind of. Yeah, okay. And of course we have to draw the other part as well. Something like this, maybe. And we remove this one, make it more dotted. That's a big gap. Yeah, this would do. Okay, stroke. Right. Okay, cool. So from your graph, determine the value of Nicola. Determine the value Nicola would find for each of the following. Planck constant, show you're working. Okay, so Planck constant is just finding the gradient. Okay, so m is equal to, I'm going to use these 2 points over here, easy because they are very close to the actual given value, so I'm just going to use them. So we have, what is it, 0.9 minus 0.5, yep, 0.9 minus 0.5, all divided by 8 minus 7 times 10 to the, what was the frequency, 14. Okay, so that is equal to, if I were to put that in, we'll get 0.9 minus 0.5 divided by 1 times 10 to the 14. So I get 4 times 10 to the minus 15 EV. Okay, so 4 times 10 to the minus 15. Alright. The threshold frequency, for that we need the whole equation because we are basically finding the x-intercept. Okay, so y is equals to 4 times 10 to the minus 15x plus c at 7, yep, 7 times 10 to the 14, and what was the voltage? 0.5. 0.5. So 0.5 is equals to 4 times 10 to the minus 15 times by 7 times 10 to the 14 plus c. So if I were to get c, our c would be 7 times 10 to the 14 and take away 0.5. So c would be minus 2.3. So our equation would become minus 2.3 here. Okay, and now we just have to find the x-intercept because that is the threshold frequency. So our x-intercept is when y is 0. So basically we are finding x is equals to 2.3 divided by 4 times 10 to the minus 15. That's what we are finding. So 2.3 divided by 4 times 10 to the minus 15. So we'll get 5.75 times 10 to the 14. Okay, so that's our threshold frequency, 5.75 times 10 to the 14. Work function of the metal. So work function is just W equals to H times FO. So 4.14 times 10 to the minus 15 times the cutoff frequency, which is 5.75 times 10 to the 14. And we are using EV, so that's why I use this just for my reasoning. So 4.14 times 10 to the minus 15 times by the cutoff frequency. So I get 2.38. 2.38. Okay. Explain what information is given about the emitted photoelectrons by the recorded voltage measurements. Okay, well, so the recorded voltage measurement give information about the max kinetic energy, because these are all stopping voltages, right? Because when the voltage is increased to the point where current becomes zero, as where is it? Yeah, until current reaches zero, that is a sign that it's a stopping voltage. So that will give us the maximum kinetic energy of the emitted photoelectrons. Electrons as E K max is equal to E times Vs, where Vs is the stopping voltage. Stopping voltage. Okay. If Nikola had carried out the investigation using a photocell with a plate made from a different metal, explain what effect, if any, this would have had on the graph drawn in figure 22 in part B, page 44. So here, okay. So since metal is changed, well, obviously, because every single metal will have different work functions, so work function would be different. And therefore, threshold frequency, or maybe I should say the x-intercept, would be different. Okay. What else? How many questions? Jeez. Okay, that's it. Good. Okay, in carrying out her investigation, Nikola initially used a green filter and produced a graph of a photocurrent this versus this. Okay. She then replaced the green filter with a blue filter. Okay. Keeping the light output power of the blue light at the photocell exactly the same as the light output power of the green light. What does light output power mean? Does it mean intensity or? I'm gonna say that this is intensity, I guess. Intensity or brightness, whatever. Yeah, I'm gonna say that it is intensity. If I'm wrong, just let me know that in the comments, yeah? So the intensity is the same. Okay. Will the position of P, as shown on the graph in figure 20, move to the left, remain the same, or move to the right? Justify your answer. No calculations on numerical values are required. Okay, well, so blue light will have a higher frequency than the green light, essentially. So the magnitude of the stopping voltage will increase. So let me just write it down. So the blue filter will emit blue light which has a higher frequency than green light, and hence the magnitude of the stopping voltage will increase. Okay, so it will move to the left. P will move to the left. Okay. Move the position this, move to the right. Okay. Okay. Will the horizontal line NM on the graph shown in figure 23 indicate a photocurrent that is greater than, same as, or lower than the line for the green light? Justify your answer. Okay, so if it's just, it will be same, right? Same, because if I were to maybe plot it, the new, when it's blue, it will look like this basically. Since I'm assuming that what they say here is basically intensity. If it's power, it's gonna be different, obviously, but if it's intensity, it's going to look like this, because intensity stays the same. It's just that the frequency is changing, so the stopping voltage will change. But apart from that, yeah. So since the intensity is the same, is kept, or maybe is unchanged, photocurrent will be the same as the horizontal line NM. Horizontal line NM. The results of photoelectric effect experiments provided strong evidence for particle-like nature of light. State one feature of the results that provided this evidence. Your response should explain why the wave model does not satisfactorily explain this feature, how the particle-like nature does explain this feature. So in this one, I'll be talking about the threshold frequency. So one experimental result that supports the particle model and cannot be explained by the wave model is the existence of the threshold frequency for emission of photoelectrons. According to the wave model, increasing the intensity of the light should provide enough energy to the electron to emit regardless of its frequency. Okay, so one experiment. Okay, existence of threshold frequency. Yep, according to the wave model, increasing. Yep. Okay, so we had to also explain. Okay. However, the photoelectric experiment shows that no electrons are emitted if frequency of light is below the threshold. Even when the intensity is high. This observation cannot be explained by wave model, but can be explained by particle model. Almost done. I just have to explain how particle like nature explain this feature. So in particle model, light consists of photons, and each photon has energy proportional to frequency, which is E equals to HF. Therefore, only the photons having higher energy than the work function can be emitted. This explains the threshold frequency, and hence, what is it? Particle, and hence provide strong evidence for particle-like nature of light. Hence provide strong evidence GG for the particle okay, for the particle like nature of light, Okay, gosh, that was a long answer. Okay, here you go. So if you guys just want to skip to this part, here's the full answer, and I think that's it for this paper. Okay, yeah, so thank you for watching this video. Hopefully you guys went well, and if this was your last exam, congratulations, you passed VCE, and hopefully you'll do good in life as well. So all the best for your future endeavors. Again, thank you all for watching, and I'll see you in the next video. Bye bye.